Okay, this is section 6.4, and we're going to look at the wave properties of matter. What we're going to talk about right now are what are called matter waves. And we're going to use matter wave, this idea, to talk about electrons, protons, neutrons, and even atoms themselves. So here's essentially what happened. This is historical. Back in the 1920s, Bohr had developed his theory of the hydrogen atom, the Bohr theory, which showed that it could be reasonable to expect that we would have quantized levels, energy levels, for the electron in the hydrogen atom. But the Bohr model could not explain more complicated atoms, like even the helium atom. The mathematics just didn't work out. So scientists were still trying to figure out what's going on in terms of the structure of the atom, explaining things like the line spectrum of hydrogen and other elements as well. So de Broglie came up with this idea, which was, he said essentially, if you think about it, if we think of light as waves, right? And we're talking about electromagnetic waves, right? So when we say light, we mean visible light or radio waves or X-rays. So we can think of light as having waves. It has a wavelength, right? And a frequency. But we can also think of light as being a particle, right? The idea of it being a photon, which it does have a wavelength, but it's actually behaving like an individual particle, a particle of light, which we call a photon. And based on the evidence, it appears as though at times light behaves like waves. So that's definitely a property of light. But under other circumstances, it might be behaving as a particle. So the issue then is, for de Broglie, is perhaps subatomic particles like electrons or protons and neutrons, which are really small, they're microscopic, maybe they exhibit similar phenomena. Maybe they are capable of acting as a particle under some circumstances and acting as waves under other circumstances. The latter part of that hypothesis was very controversial. The idea that an electron or a proton could behave like a wave was a pretty new idea, and it would take some evidence to get people to agree to that. But de Broglie, he essentially said the following. Consider it this way. You know that the electron is stuck to the atom in some way through the electromagnetism, right? There's an electrostatic force holding the electron to the proton. But there's some sort of motion going on for the electron around the nucleus. So he said, here's an analogy. Consider a musical instrument, like a guitar, right? A stringed instrument. What happens in a stringed instrument is that when you apply a force downward or upward, the energy that you're putting into that string is transmitted through the string in the form of a wave, a vibration, right? And there are only certain frequencies or wavelengths that are allowed for those vibrations. So for example, when you pluck a string of a guitar, it doesn't give off all frequencies or all wavelengths. It only gives off some, a fundamental, an overtone, a second overtone, so forth and so on. Now mathematically, what happens with the guitar string is the allowed wavelengths of the vibration are connected to the length of the string itself. They are multiples of a half of the length. So if you look in this picture, in this diagram, you'll see that 3 different wavelengths are allowed. Half the length of the string 2 halves of the string and then 3 halves of the string. Only those are allowed. So De Broglie said, well, wait a minute, an electron is not linear, or an atom is not linear. The electron is not undergoing some sort of vibration in like a line, along a line, like in a guitar string. The vibration is more like akin to a circle, a circular vibration. So on the right, what you'll see are 3 vibrations. We can think of these as vibrations of the electron. And those could perhaps be allowed vibrations of the electron. And what De Broglie said was that if you consider, here's the nucleus at the center, and then here's the electron some distance away, there's a radius, right, a radius of that electron from the nucleus. He said essentially that 2 pi r, which is the circumference of a circle, right? 2 pi r is just the circumference of the circle. 2 pi r has got to be some multiple of an allowed wavelength for the electron. So this would be the wavelength of the electron. So now he's claiming essentially that the that the electron has a wavelength. There's some inherent property of the electron that it has a wavelength. Okay, this would be just a multiple. 1, 2, 3, 4. Okay, think about that. When Bohr introduced his idea of the hydrogen atom, he also introduced this idea of some multiples, right? The energy levels, 1, 2, 3, 4, and so forth and so on. So essentially, De Broglie is saying that this multiple times the wavelength of the electron, some inherent property of the electron, is got to be equal to 2 pi times the radius of the orbit that the electron is in, okay, which is the circumference. So shown in the diagram over here, part B, 2 allowed for n equals 3 and n equals 5, 2 allowed vibrations are shown. And then there is 1 forbidden or unallowed vibration where it's 3.5 or something like that. So that's not allowed. That vibration would not be allowed. Okay? So that's essentially De Broglie's idea. And he took it further to say that, hey, if we go through a consideration of momentum, we could find that the wavelength of this electron, the inherent wavelength, would be equal to Planck's constant, h, divided by what's called the momentum. So I'm going to put mu for momentum. Mu is the mass of the electron times the speed or the velocity of the electron. And that's called the linear momentum. Mass times velocity, or just momentum, okay? So what he said was that you could actually figure out, based on knowing the mass and the speed of the electron, you could figure out what this wavelength is. And as I said, this was quite controversial. De Broglie put this out as a proposal for his doctoral thesis, and the people on the committee, some of the people on the committee at least, were very much against this idea. And so what happens then is, not too far after he puts out this idea, within a couple of years, an experiment is done. And this experiment, using X-rays and electrons, shows that the behavior of electrons is not all that dissimilar from X-rays. So over here on the left, this is what's called an X-ray diffraction pattern. The bright spots are where you get constructive interference of the X-rays that are essentially reflected off the surface of a metal. And so the pattern, these rings around the center, are what you get when you have waves interacting with the surface. On the right are electrons impinged on the surface of the same metal. And so what you see on the right is a very, very similar pattern. Again, those rings indicate, that pattern indicates that this is a wave-like property. Diffraction is a wave, a property that waves possess, not that particles possess. So this experiment very quickly showed that there was some truth to de Broglie's idea, that in fact, at the atomic level, these particles that we think of as, little balls moving around, maybe in a circular motion or a spherical motion, are actually can behave like waves under proper circumstances. And so we call them matter waves. And what you can see is that the wavelength of these matter waves can be calculated. And if the wavelength of one of these matter waves is close to the wavelength of an electromagnetic wave, like an X-ray, then some of the physical properties, such as the X-ray diffraction pattern, will be essentially replicated in the case of using these subatomic particles.